Yeah, so this is module 12. It's about IPv6 addressing. So through this session, we are going to be covering about IPv6. So IPv6, it's just that version of address that actually it's that advanced, or it's a successor of IPv4. IPv4 because of the space. So IPv6, it is in existence because of IPv4, it's out of the space compared to devices that are in need of IP address. So when you compare IPv4 address and then the demand of devices that are in need of IPv4, that are in need of addresses, IPv4 cannot handle. So topic to cover issues with IPv4, then representation of IPv6 address, then address, IPv6 address types. Then we have global unicast address and link local address static configurations, how to assign these IPv6 addresses statically. And then we have called dynamic addressing for IPv6. So the module objective, implement IPv6 addressing scheme, and then within this we're going to look at dynamic addressing, implementing IPv6 addressing, and then other dynamic addressing for IPv6 local link address, then IPv6 multicast address, and then subnet and IPv6 network. So issues with IPv6, IPv4 is running out. IPv4 is running out. IPv6 is the successor to IPv4. So IPv6 has a much larger 128-bit, meaning that if you have to get the total number of supported IP address, it's 2 power 128. Then within IPv4, it's 2 power 32. This. Okay, so the development of IPv6 also included fixes for IPv4 limitation and other enhancements. So with an increasing internet population, a limited IPv4 address space, then issues with NAT, with an increasing internet population, because now with internet population it has increased. And then we have the issue of IPv4 address space, that IPv4 addresses are few. Then issues with NAT, that within IPv4 we have what you call private and public. So the private as translated to public IP address every time the internal computers wants to access internet. So it's an issue. And then the IoT. So IoT, it's Internet of Things. That there are so many devices that traditionally they used not to. They used not they used not to be assigned with IP addresses, but this time they are assigned with IP addresses, or they were transitioned to network devices. So they come into that class, or that category of Internet of Things. Then time has come to begin transition to IPv6, because for it has enough address space. Enough address space. So IPv4 and IPv6, they can actually coexist. They can coexist. So both IPs coexist in the near future, and transition will take several years. So it's not that if you want to transition, you just switch immediately from 4 then to 6. But these two, they can coexist on a single interface, on a single interface, and then the transition will just come slowly, come in slowly, which can take several years depending on the depending on the absorption way mode. So the modes, we have dual-stack, we have tunneling, and then translation. The modes on how these two versions can coexist. So with dual-stack, the two addresses are assigned on a single interface. Then tunneling, packets of IPv6 are sent over IPv4. That IPv for this side it's 4 and then 4, but in we have a tunnel that uses IPv6 and then IPv6. Then transition, so translation, one side it's 4 and then the 6, then the other side it is 4. So every time IPv4 packets are trying to close the what we call NAT64 device, then they translated to IPv6 package, and even the reverse is true. It's true. So note, tunneling and translation are for transitioning to native IPv6 and should only be used where needed. So the goal should be native IPv6 communication from source to destination. So these are the modes on how the two versions can coexist with time, so that when time comes, the transition can be fully absorbed from 4 then to 6. So the network representation, IPv6 are 128 bits in length and written in hexadecimal, and IPv6 address are not case sensitive, so you can write A or you can write it in lower case. So IPv6, a extent is an official term, or an official term used to refer to segment of 16. So the extent, it is this, and it's a segment of 16 bits. And it's the official, the technical name. So this is an extent, and it's a segment of 16 bits. So here there are how many? Here 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 extents. So as you're writing IPv6 address, you have to make sure that you have 8 extents. So these are the two examples, and for you to master this, you can even go ahead and try to formulate yours. Formulate your IPv6 address different from this, but borrow knowledge whatever that we have here. IPv6 address representation, we have the rules, because when you look at this address, it's the address, it's long. So to compress this, there are rules. That rule number 1, with rule number 1, we're going to omit the first rule to reduce the notation of IP address is to omit any leading 0. For example, if I have 01, then it is equivalent to 1. If I have 001, it is still the same as 1. So we're omitting these leading zeros. So here, if you have this, then we can omit this. That is what we have here. If you have this, we can. If you have this, we're going to omit this. Not that you have to omit this is the leading 0, and you stay with this, then this. So in other words, if I have 0010, then I will omit this and remain with this. So if I have 0, 0, 0, 0, then automatically, because we are omitting leading 0, I will omit all this and then my extent remain with a 0, like that. Yeah? So we have this, we can omit this, you stay with. So here we have an example, and it's here. See, if you have to go by that rule number 1, omit leading 0, so we're going to omit this 0 here, and then this 3, we omit this, and this, and this, then this, and then we remain with this. So when you look at the format so far, what we have, it is a bit simpler. It is a bit easier for someone to memorize that address. So let's go next. We have another rule. We have another rule. So this other rule, double, it's going to bring in what you call double colon. Double colon this. That we had colon, but this time we're going to bring in double colon. Can replace any single and contiguous string of one or more 16-bit 16-bit extent consisting of all zeros. So in scenario where we have a zero, like this, we have already used, actually the address has already passed through rule number 1. So if you have this leading zero, for example, let's assume that here we have a 1, maybe this side we have A. So these are the single and contiguous string of one or more 16 extent consisting of zeros. So we are going to compress this by removing all of this, because now when we remove all this, what do we remain with? We have the 1 here with this, and then we have this here with this. Then at the end of the day, we have our 1 here, and then another here, and then A. So this is how we use the second rule. So here we have our preferred IPv6 address with 8 extents. This is 1, 2, 3, 5, 6, 7, then 8. So we're going to omit the leading zeros first. This one here out, this out, this out, then this out, then this out, and then this out. But we have this, what we call the single, because this is a single uh, extent with a zero, but contiguous. There is another one that follows it, and then another one follows it. So we're going to extract all these, and then we remain with the double colon. So now the double colon is going to come in between here. So we have our 2001, then DB8, then we have a 0, which is this. Then we have 1s here. Then here we are extracting all these, and then we remain with the double colon with 2, 0. So this time, how many do we have? We have 1, 2, 3 here, 4, then 5. Now, where we have the double colon here, the missing extents, the other 3, because these are 5. Now, the missing extents means that there will be zeros and they will be fixed here. It's like when you have 0, 1. Automatically, if it becomes a 1 here, if you to add a 0, you will not add a 0 this side. Because if you add a 0 here, it will change the meaning. It will change the decimal value or the position value of a 1, and it becomes into the position of tens. And yet it's supposed to be in ones. But automatically, if I want to add in a 0 to it, it will be 0, 1. But since this is a 0, it won't change the meaning. Even if you get 0 times 10,000, it remains as a 0. So this is rule number 2. So we have what we call IPv6 address types. There are three broad categories of IPv6 address where we have unicast, multicast, encast. In IPv4, we have still this unicast, then multicast, and then broadcast. But in IPv4, we don't have a broadcast. Instead, we have any cast. So any cast here, this is any IPv6 unicast address that can be assigned to multiple device. So a packet sent to any cast routed to the nearest device having the same address. So if it's this PC sending, we have this as the 2, we have this as the 3, we have this as the 4, we have this as 5. So there is a possibility that those computers that are close to the sending device, they're the ones to receive any cast. Okay? The closest IP addresses are the ones to receive. So like I said, that IPv6 does not support broadcast. Instead, there is any casting. We have what you call the prefix lengths. The same way in IPv4. IPv4, we have what you call network portion and then the host portion. So when it comes to IPv6, we have a prefix. This is a prefix. And then when it comes to this side, it is interface ID, period. So with IPv6 still, there must be the network, what you call the prefix, and of which that prefix, it remains constant. Then the interface ID, it's the one that keeps on changing. It means that that space, it is available for hosts. We have an example here where we have, this is how it is abbreviated, this. Now, actually, this, it can be like an exercise, that we have this and we are to abbreviate it. How are we going to abbreviate it? It's 2 of D, B, H, and then this, we have A, and then when it comes to this, because it's 1, 2, 3. This one here, this side, as you can see, they're supposed to be 4, but since this one here, it's also part of these zeros, we're going to abbreviate them. And then the prefix length is 64. So in other words, the 64 bits here, they have to be uniform, meaning that it will bring in the zeros here, because this is, here we have 16, 16, /64. So all these, they have to be uniform, and then these other 64, they are the ones that are zeros to keep on changing. Types of IPv6 unicast and unicast. The unicast, these are what you call the single, the IP address is the unicast address, the one that can be assigned to interfaces. Assigned to interfaces. So we have what you call unlike IPv4 address that have only single address. IPv4, it has single address, but IPv6 address typically have two unicast. So we have global unicast address and then link local address. So global unicast address and then link local address signed under the same interface and their IP address, which is not the case when it comes to IPv4. It has with IPv4 it supports only one, but with IPv6 it can support two addresses here. So global unicast address, this is similar to public, public IP address, public IP address. Then link local address required for every IPv6 enabled device and are used to communicate with other devices on the same link. So if I have a PC here connected to the router, and then this router connected to other PCs. So this is PC1, this is PC2. So we have two interfaces. We have A here and then B. Then we have C here and then D. So link local addresses, they are used, what this statement means, that link local addresses, they are used on point-to-point here. The point-to-point, or they can be used locally in scenarios where you have a switch. Let's assume that this is a switch and you have computers like this. Here you have A1, you have A2. The linked local address assigned here, it can be used to reach A2, it can be used to reach B this side. So this is locally. It is locally. Is used locally. So linked local addresses are not routable and are confined to a single link. You see now, confined to a single link, which is this. So here we have the IPv6 unicast address, we have global unicast, we have linked local, we have loopback. Now these are special, loopback and a specified address, unique. Now unique local, these are, when it comes to unique local, these are uh, private, the ones that are equivalent to private IPv4 address. So note about unique local address. Uh, Unique local addresses range from this, ranges from this, from FC00, then to FD, FF. Okay, so this unique local address ranges in this range, and it has some similarity at private addresses for IPv4, but there are significant differences. So unique local addresses are used for local addressing within site or between a limited number of sites. Unique local addresses can be used for devices that will never need to access other network. Unique local addresses are not globally routed or translated to global IP address. Note, many sites use private nature of addresses to attempt to secure or hide the network from potential security risks. Most of the time that originate from outside the network or an external network. This was never intended as uh, intended use of unique addresses. So the range, I just wanted to shed more light on this, shed more light on this. Um, I have here we have the address. Now, if we talk of the range, it means that the start, the start, you can have this, this, it's a must. It has to start from this. And then be this, this. And the slash, as you can see, we have /7. We have /7. What does this mean? What does this mean? That when you look at this, when you convert this, yeah, okay, we're saying that /7 here, they have to be the same from the start up to the last. But when you look at this /7, now that, because as you can see, it is a range. It is a range. So choose this, it will be 1, 2, 4, this one here. If I convert 7, so F, it gives me 4. Then the C, it's a 12. The 12. And a 12, it's then views. And then when it comes to this one here, if I convert this, so the 7 will be this and then up to this. So when it comes to this, still, I will just copy this to save time. That F here, it's this. Then D is D is it is 13. So 13 meaning that this equals to it's 13. So it is 12. So it's 8, then 4, 12, and then a 1. But as you can see that the prefix links, they are saying that what is supposed to be uniform, the 7 bits. How many are the 7 bits here? These are 6, then this is 7. You see this now, that we have 7 bit, and even here, the 7 bits are there. So that is where the 7 is coming from. That these 7, these ones here, they have to, but the rest here, these are the rest here. So the start, it's this, and then as you have to keep on affecting them, because this is a D. So these other ones, they can change. Remember, we have this, the 2. And then when it comes to this one here, as you can see, this, that it's also F, F, F. So you can change from this as here the difference is, the only difference that I'm saying here is from C. So it changes, this is a C, then a D. So it has to change to this. So in other words, it's this and then this one here. That is the range. And these are so many IPs. Then we have uh, uh, global unicast, uh, global unicast address. These are global unique. Now something that is global, this is public, unique, and routable. So currently, unicast addresses with the first 3 bits, 3 bits, or this, or this, first 3 bits I use being assigned. Currently available, this begins with decimal 2 or 3. Any IPv6 IPv6 address that begins with either 2 or it's a global unicast address, period. As long as an address begins with, for example, if I change this and give it a 2 like this, then this is a global. If I give it a 3, still this is our address, the previous address. So if I change this and give it a 2 instead of F, as you can see, touching with the 2, it qualifies to be a global unicast address. If I say 3 like this, it also qualifies to be global as to it qualifies to be it qualifies to be be IP global unicast IPv6 address. So as you can see there, we have the range because now we have a 2. So if you convert, because we're saying a 2, either a 2, if you have a 2 and you convert into binary, a 2, remember what you're seeing here, these two, this in binary, it is 0, then 1. It is a no. No. Like this, like that. So this side, of course, we expect this like this. So this one here is our 2. Then a 3, a 3 is in this format, like this. So here we have, remember, it is /3. I want to show you where the 3 is coming from. Where is the 3 coming from? So when you look at this, the 3, it means this. That the first 3, look at this, that the first, this 1, 2, 3. And then even here, this 1, 2, 3. But when you look at this, you cannot consider this because this one here, it is not available here. So here, this, it has to be uniform. The first 3 bits, they have to be uniform. That is what it means, +3, this. So anything that begins with this, like I said, it can either be a 3 or a 2 here. So it qualifies to be a global unicast address. So they are here. So when you look at this, that the start is this, and then the last is this. But both the start and this are the same. That is where the /3 is coming from. With global unicast address, it has three portions, sections. We have global routing prefix, then subnet, and then interface ID. This is the same as host. But the subnet ID, once you have the global routing prefix, you can maintain this, and then if you want another network, you keep changing this subnet ID, as we're going to see in other slides. So the structure, we have global routing prefix is the prefix, so you can call it network or portion of the address that is assigned by provider such as ISP to, to a customer or a site. So the global routing prefix will vary depending on the ISP policy. Then we have the subnet ID. Is the field is the area between global routing prefix and the interface ID. The subnet is used by an organization to identify subnet. So once this one here is assigned by the service provider, then the subnet ID is also available now to be used by organization to identify the subnets. And then we have interface ID. The interface ID is equivalent to host portion in IPv4 address. And it is strongly recommended that in most cases it should be 64 subnet. The cases 64 subnet should be used, which creates 64 bits interface ID. So the 64 indicates, in other words, we have 64 for both. Actually, when it comes to this one here, this, it's 48, and then the subnet ID takes 16, and then this takes 64. So this one here it uniquely identifies a subnet, and then this uh, uh, the, 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 uh, the subnet, sorry, the ISP, the ISP. So we talked earlier along. We talked about link local address that it can be used, as you can see, on point-to-point or on a local network here. It enables device to communicate with other IP-enabled device on the same network and only on that link or subnet. Packets with a source or destination link cannot be routed, can't be routed or accessed on public network. Every IPv6 enabled network interface must have, so every time you enable IPv6, then this link local address is enabled automatically. If a link local address is not configured manually, on will automatically create one, and in this format. In this format. What does this mean? That it's /10, we have to convert this into, so F, uh, F, F is all ones, FE, which is 14, H, then 4, 12, and then 2. Then we have 8, so 8 is 1, then 30. The range here, the bits, the constant bits, they're supposed to be 10. So this is 4, this is 4, and then this. So all these other ones, they can change, but it will always remain like, if this change, if this all changes, the range it will be, because if this one here changes, and then this, 10, then 11, so B, up to B. So it will F, E, F, E, B. to be, yeah, it is up to be something like that. Where is the 10 coming from? You just simply count this. So it has to remain uniform. So every time you see F link, local link. So for that option, we're in